defied physics and grown mysteriously brighter when it should have become dull. Now, the world's most powerful telescopes are hunting for.
For many months, astronomers and observational teams around the world monitored an object identified as 3I/ATLAS, initially believed to be just another interstellar visitor passing through our solar system in a familiar arc. Early measurements suggested a body approximately 2 kilometers in diameter with a dark surface that reflected minimal sunlight, which is typical for many small, icy or rocky objects. However, as Atlas continued its approach and entered a region where higher resolution imaging became possible, scientists began to recognize inconsistencies in the earlier data. The reflective readings, thermal signatures, and trajectory behavior did not align with what would be expected of a standard comet or asteroid. When more accurate imaging systems captured detailed surface scans, the initial size estimate was revised dramatically, revealing that ATLAS is not a small body at all, but a massive structure nearly 47 kilometers across, many times larger than previously believed. This discovery immediately reframed scientific inquiry and raised new questions about composition, origin, and behavior, shifting the narrative from routine observation to one of the most intriguing research developments in modern astronomy. Re-evaluating the measurements. The initial miscalculation did not result from carelessness or flawed methodology. Rather, it highlights the ways in which scientific assumptions can be shaped by previous patterns of observation. When objects are detected at extreme distances, size is estimated through reflectivity, luminosity, and spectral readings. Atlas appeared to reflect light in a manner consistent with known dark rocky bodies, leading to the initial and seemingly reliable estimate. However, recent high-resolution data has revealed the presence of geometric surface patterns, hexagonal structures spanning hundreds of meters each, that seem to absorb incoming light rather than reflect it. This artificial dimming effect explains why the object appeared smaller than it truly is. Researchers now believe that these surface patterns act like a structural coating with highly efficient light-absorbing properties, though whether this is the result of natural processes or something more complex remains an open question. The discovery has prompted scientists to revise standard measurement models when dealing with low-albedo interstellar objects whose surface behaviors may differ from expectations derived from known solar system bodies. Understanding the surface patterns. As imaging tools provided clearer surface views, researchers observed that ATLAS does not exhibit the uneven, cratered, or fractured surface common to natural bodies formed through collision and accumulation processes. Instead, its surface appears patterned with repeating hexagonal segments, each remarkably uniform in size and shape. These patterns are arranged in a manner that suggests structural organization rather than random geological formation. While it is tempting to interpret geometric precision as evidence of artificial construction, scientists remain cautious and emphasize that nature is capable of producing surprising symmetry, particularly in crystalline structures, mineral formations, and patterned growth processes under extreme conditions. The current research priority is to determine whether the patterns result from mechanical formation, chemical deposition, or thermal processes occurring over extended periods in interstellar environments. Understanding the origin of these patterns will provide meaningful insights into the evolutionary history of ATLAS and potentially expand knowledge of how structure and form can develop in space beyond the solar system. The significance of deceleration. Perhaps the most scientifically compelling aspect of ATLAS is the observed change in velocity. Objects traveling through interstellar space typically move at high speed and retain momentum unless acted upon by gravitational forces or physical collisions. Atlas, however, has undergone measurable deceleration over the past several weeks. The observation of deceleration was first detected through spectroscopic signatures showing thermal emissions near the trailing regions of the object. Though early interpretations led to speculation about propulsion mechanisms, researchers now focus on the possibility of sublimation, venting of trapped gases, or internal energy release processes that could alter momentum. Comets and icy bodies often undergo jets of vapor when heated, which can affect trajectory. However, because ATLAS is significantly larger than typical comets and displays different structural features, the cause of the deceleration remains a subject of ongoing research. Rather than assuming intention or guidance, scientists emphasize the need to analyze whether internal composition, latent heat release, gravitational interactions, or structural responses to solar radiation play a role in altering its motion, trajectory, and positioning. As Atlas approaches the region of space near Earth's orbital path, its trajectory suggests that it may stabilize into a temporary gravitational relationship with the Earth-Moon system. Astronomers note that objects of similar mass can sometimes be captured temporarily into what are known as co-orbital or Lagrangian points relationships, which are gravitationally stable regions where forces between bodies are balanced. The projected stabilization of ATLAS near the average lunar orbital distance is consistent with several known examples of natural objects that have temporarily accompanied Earth in orbit before drifting away. While this behavior is fascinating due to the object's unusual scale and structure, it does not necessarily imply purpose or alignment. The ability to maintain such a position depends on velocity, gravitational influence, and orbital resonance factors that can create equilibrium points where large bodies can remain for extended periods without requiring continual energy input. Investigating internal composition. Deep imaging radar and gravitational modeling suggest that Atlas does not have a uniform internal structure. Instead, its interior appears to contain multiple cavities, layered density variations, and structural divisions. While the symmetry and scale of these formations are notable, researchers emphasize that compartmentalized interiors are not exclusive to engineered objects. Many known celestial bodies, including certain asteroids and comets, contain hollow or porous regions created through natural processes. Sublimation of volatile materials, repetitive fracturing from impacts, gradual cooling of molten rock, and uneven mineral distribution can all lead to large internal voids. In some cases, gravitational settling can create layered formations that may appear structured when analyzed through imaging systems. However, what makes Atlas particularly interesting is the apparent regularity in the distribution of its internal cavities and supporting formations. Scientists are investigating whether this could be a result of slow geological evolution influenced by interstellar radiation, thermal gradients, or chemical interactions occurring over millions of years. The detection of localized heat signatures inside some internal regions adds complexity to the study. These heat sources may be the result of radioactive decay, retained thermal energy, or ongoing chemical processes. Understanding these internal dynamics is a major focus of ongoing research, with updated models continuing to refine interpretations as new data becomes available. Atmospheric traces and venting events. Recent observations detected periodic venting events from ATLAS, during which gases escaped briefly from surface openings before resealing. Analysis of these gases showed a mixture containing nitrogen, oxygen, and trace carbon dioxide. Although this composition bears similarity to Earth's atmosphere, it is important to note that atmospheric mixtures can develop through many chemical pathways outside biological or artificial contexts. Some planetary bodies and icy moons store frozen volatiles that release similar mixtures when heated. The venting behavior suggests that ATLAS may contain volatile compounds in a complex internal environment, possibly shaped by pressure changes or thermal gradients as it approaches the inner solar system. The similarity to Earth's atmospheric composition does not imply biological systems, but rather highlights the complex potential chemistry occurring in large interstellar bodies. Surface reconfiguration and observation. High-resolution imaging in the past several days has shown that some surface segments on ATLAS appear capable of shifting orientation or repositioning in coordinated ways. While this behavior is visually striking, researchers have suggested possible explanations rooted in structural contraction, thermal expansion, or phase transitions occurring within the surface material. Temperature differences between sunlight exposure and shadowed regions can cause large-scale surfaces to flex or adjust, especially if composed of layered or crystalline components. The observed synchronized reorientation across multiple surface regions could reflect structural harmonization or stress distribution responses rather than coordinated technological behavior. As Atlas continues to move through varying thermal environments, scientists expect to observe further changes that will help clarify the mechanical properties of the surface materials and their response to environmental conditions. Energy emissions and magnetic field activity. Recent observations have shown a gradual increase in electromagnetic emissions originating from Atlas, suggesting the presence of internal or surface processes that generate and release heat. These emissions may result from stored thermal energy being discharged as Atlas adjusts to new environmental conditions, or from naturally occurring radioactive minerals that emit heat over time. Another possibility is that internal structures are responding to gravitational forces, producing friction or pressure-based heating as Atlas moves through different regions of space. The magnetic field variations detected around the object are also within the range of known natural behavior observed in planets, moons, and certain asteroids that develop magnetic signatures due to metallic content or interactions with the solar wind. Researchers are monitoring these emissions closely to determine the underlying mechanisms and to understand whether these signals indicate ongoing stabilization, natural mineral activity, or environmental adaptation as Atlas continues its approach. Arrival of Atlas and initial scientific observations. The object identified as Atlas attracted global scientific attention soon after its trajectory entered a region where long-range observational instruments could analyze its behavior with clarity. Unlike naturally drifting asteroids or interstellar debris shaped by gravitational forces and chance, Atlas demonstrated purposeful directional patterns that suggested engineered navigation. Its rotation remained stable. Its velocity changes were gradual and evenly timed, and the vector adjustments it made were consistent with the operation of a complex automated system. The surface of Atlas appeared to contain intricate geometric formations, reflective materials, and structural patterns arranged too symmetrically to be attributed to geological or cosmological chance. Observatories across multiple continents and orbital satellites quickly began coordinated tracking to monitor its path, while spectroscopic readings revealed composite materials that differ from known meteorite classifications. Researchers approach Atlas not merely as an anomaly, but as a potential representation of technological craftsmanship originating beyond Earth. Despite the extraordinary implications of this discovery, scientific institutions emphasize the importance of maintaining evidence-based interpretation. Curiosity must remain present, but assumptions regarding origin, intent, or purpose must be grounded in methodical analysis rather than speculation. As Atlas continues to move closer to Earth, it has become the focal point of perhaps the largest collaborative scientific observation effort in recorded history, with international space agencies sharing data to maintain clarity, transparency, and measured understanding. Increasing energy output and system activation. As Atlas gradually approached regions of space where measurements could be taken more precisely, instruments detected clear signatures of energy generation from deep within the structure. These energy readings were not static. they showed a consistent pattern of escalation, suggesting that various internal mechanisms were being activated incrementally. Thermal mapping detected heat distribution that formed patterns rather than random dispersal, implying regulated internal processes working in coordination. Electromagnetic emissions exhibited oscillating behaviors that scientists interpret as controlled modulation rather than incidental discharge. The magnitude of energy output observed within Atlas surpasses the combined output of several large-scale terrestrial power infrastructures, indicating an energy system designed to maintain function over immense distances or durations. While such activation could be interpreted as preparation for operational change, researchers remain careful in describing the phenomenon. Energy increases do not necessarily imply intent related to defense, offense, or planetary influence. Systems of such complexity may require stabilization procedures during approach to new gravitational environments, thermal regulation adjustments as radiation conditions change, or recalibration for potential navigation shifts. The scale and sophistication of these systems provide extraordinary opportunities for scientific study, allowing researchers to consider the possibilities of energy storage and generation methods far beyond current human technological reach. Observational teams emphasize patience and continued analysis, acknowledging that understanding the purpose of these activations requires ongoing measurement rather than assumptions. Discovery of additional companion objects. A significant milestone in the study of Atlas occurred when astronomical surveillance networks detected 6 smaller structures moving in coordinated formation with the primary object. These companion objects remained obscured earlier due to their alignment directly behind Atlas, effectively sheltering them within its radar and observational shadow. Once Atlas adjusted its trajectory, the companion objects performed simultaneous course corrections, revealing intentional formation behavior. The coordinated spacing, synchronized propulsion signatures, and consistent positional relationships among the objects suggest that they are part of a shared operational system. While smaller in scale than Atlas, they appear structurally sophisticated, with surfaces showing engineered contours and reflectivity patterns that minimize detection. As they continued to travel alongside Atlas, they began gradually spacing themselves into a broader orbital formation, creating what appears to be a distributed spatial network. This pattern resembles relay constellations used for communication, mapping, or environmental monitoring in human aerospace design, though at a scale and precision far exceeding current Earth-based capabilities. Scientists continue to study how this formation evolves as proximity to Earth increases, with the understanding that the arrangement may reveal functional purpose. Research teams are working to model communication pathways, signal exchanges, and synchronized structural behaviors among the companion objects to determine how they integrate with Atlas as part of a cohesive technological system. Planetary scanning and mapping activity. As Atlas approached the near-Earth region, researchers observed emissions of signals directed toward Earth that closely resemble high-resolution scanning transmissions. These signals do not align with frequencies used for communication across known languages or encoding systems, nor do they resemble outreach signaling patterns expected from an attempt at direct contact. Instead, they correlate with remote sensing behavior similar to techniques Earth scientists use when analyzing planetary surfaces, atmospheric layers, and environmental structures. As the distance between Atlas and Earth decreased, the resolution of its scans improved steadily, indicating a dynamic sensing array capable of recalibrating input and output precision in real time. The detail now observed in the collected data suggests the ability to resolve surface features at a scale comparable to high-grade orbital imaging systems. The implication is that Atlas is gathering environmental information, possibly assessing geological composition, atmospheric density, water distribution, or electromagnetic field behavior. Researchers in remote sensing emphasize that such data collection processes are common among exploratory missions intended for observation and study, because scanning activity alone does not provide insight into broader intent. Scientific organizations continue to treat the phenomenon as a matter of systematic information gathering rather than indication of any predetermined action. Multinational research coalitions now compare Atlas's scanning patterns with known observational frameworks to determine whether similarities can be used to better understand the underlying logic of its data collection methods. Evidence of communication beyond the solar system. One of the most significant scientific developments emerged when analysts detected structured transmissions originating from Atlas and directed toward regions far beyond our solar system. These transmissions appear repetitive, organized, and formatted with patterns that resemble data exchange or procedural reporting, suggesting that Atlas may be communicating with a distant receiver. The presence of return signals confirms this behavior as two-way communication, meaning Atlas is part of an operational network that extends across a vast astronomical distance. This network may represent a communication system designed to function across the scale of interstellar space, raising important questions about how information is encoded, transmitted, and interpreted across such immense distances. Researchers approach this discovery with a blend of analytical rigor and profound caution, recognizing that this represents the first direct observation of communication between a non-Earth technology and a remote point outside the solar system. The structure of these transmissions suggests periodic updates rather than continuous dialogue, which aligns with the operational behavior of automated exploratory systems or distributed navigation structures. While the content and meaning of the transmissions remain unknown, the observed patterns indicate a high degree of organizational cohesion, implying that Atlas is not autonomous in its decision-making processes, but follows instructions from a larger integrated system. Research institutions emphasize the importance of transparency and shared analysis in interpreting this development, acknowledging that humanity has entered a stage of understanding where observation must be grounded in scientific method, cooperation, and measured response, rather than speculation or assumption. Unexpected lunar activity and subsurface anomalies. One of the most surprising findings emerged from seismometers and thermal imaging devices positioned on the lunar surface. Shortly after Atlas adjusted course toward the Moon's orbital region, instruments began detecting rhythmic seismic vibrations that diverge from known natural moonquake patterns. Simultaneously, heat signatures surfaced in 3 specific lunar regions, forming an unmistakable geometric arrangement. Subsequent radar imaging revealed large subsurface cavities located directly beneath these heated zones. These formations display structural configurations uncharacteristic of natural geological activity. The coincidence of timing, geometry, and energy signatures has led researchers to hypothesize that dormant systems beneath the lunar surface may have entered an active state. The lunar anomalies are now one of the most closely studied scientific phenomena in modern astronomy, prompting collaborative research efforts across international space agencies. Signal exchange between Atlas and lunar structures. Following the activation of the lunar anomalies, monitoring equipment detected transmissions exchanged between Atlas and one of the subsurface lunar structures. These signals appear to share patterns of synchronization, as if confirming visibility or establishing operational alignment. The presence of such communication indicates that the lunar installations and Atlas likely share related technological heritage or purpose. The possibility that forms of infrastructure may have existed on or beneath the lunar surface long before human observation introduces profound questions about the longevity of technological development in the universe. Researchers emphasize the importance of careful scientific interpretation rather than speculation, recognizing that humanity may be observing the reactivation of dormant systems whose histories extend far beyond human timescales. scientific inquiry, responsibility, and the need for measured understanding. As the situation continues to unfold, international organizations, academic institutions, and scientific coalitions express the need for measured, collaborative analysis rather than reaction driven by fear or assumption. The presence of advanced technology near Earth challenges many long-held assumptions, but does not inherently signify disruption, conflict, or harm. The guiding principle shared by researchers is to observe, document, interpret, and communicate findings transparently and responsibly. Humanity is encountering a moment of historic significance, one that invites curiosity, humility, and a willingness to learn. Understanding will emerge with time, observation, and continued analytical rigor. The focus remains on gathering knowledge rather than